Okay, nice. Are you able to see the presentation? Very nice. Let us wait 30 seconds or something so that other people can join. Okay, so how are you, Sean? How are you, Sahil? So, have Sahil, good evening. Have you revised the previous sessions that we have done? Have you revised the previous session that we have done? Okay, so how was it? Like, are you able to solve previous year questions or not? Okay, okay. Sahil, are you able to solve previous year questions? Are the concept clear? Okay, very nice, very nice. I'm very happy that you are able to solve previous year questions. Okay, so once you are able to solve previous year questions, then that means your concepts are basically covered. Okay, but now you need to do more practice. How will you do more practice? Take out more and more questions from books, from any other source, workbook, anything, and start solving those questions. It's very important that you solve as many questions as possible. Okay, it's very important. Okay, so start solving more and more questions. Yes, chalo. Let us start. So what we are going to do, generalized heat conduction equation. Why generalized? We are going to see why do we need to study generalized heat conduction. Okay, when we studied Fourier's law, we made some assumptions. Similarly, for Cartesian coordinate, cylindrical coordinate, spherical coordinate, we assumed few things, but now we are going to remove those restrictions and we are going to see what is how the generalized equation looks like. At any point of time, if my this PPT or my audio goes, just let me know so that I will reset it or something I'll do. Okay, chalo. I hope you all know me. Okay. So I have done MTech from IIT Kharagpur. I have done MSc in Polytechnico di Milano. I have more than 5+ years of teaching experience. And my AR score was 675. Okay. In 2015 or something. Chalo. Now, so should we start? Let us start. Say yes or no. Should we start? Chalo, chalo. बहुत अच्छे. Very nice. So when you remember, I don't know if you remember, but you are saying that you have revised it. So you have revised it. So you must remember that when we started Fourier's law of conduction, I showed you these 5 assumptions, isn't it? I showed you these 5 assumptions. Now I said, first of all, we are going to assume steady state heat conduction. What does steady state means? The temperature is not a function of time. Temperature is not a function of time. But what happens when temperature is a function of time? That means temperature of the body inside the body or outside the body, it means at the boundary, temperature is changing with time. So whenever change temperature is changing with time, it is called as unsteady flow heat transfer, unsteady flow. And it actually means that energy in is not equal to rate of energy is not equal to rate of energy out. That means some energy will also be stored in the body. Okay, so that will change the internal energy of the body, because any mass stores energy in the form of internal energy. Okay, so that means if energy in is not equal to energy out, the internal energy of the body will change. Chalo, theek hai. Second assumption was unidirectional heat conduction. Unidirectional. Why? We said that the heat transfer is only happening in x direction, only in x direction. But for example, temperature is also changing in y and z direction, not only x direction. So that is called as three dimensional heat transfer. It is called as three-dimensional heat transfer. Now the temperature is not just changing in x direction, it is also changing in y and z direction. Okay. Now the third assumption, we assume that no internal heat generation. There is no heat generated inside the body. But what will happen if Q dot generation is not equal to 0. It is here we are assuming what? That Q dot generation is equals to 0. But if we are saying there is heat generating inside the body, that means Q dot generation is not equal to 0. So that means with heat generation, there is a heat generation inside the body. Okay, and other assumptions are there, but these are three main assumptions. So if these things are happening, for example, temperature is varying with respect to time as well, that means unsteady, or temperature is varying in y and z direction as well, or there is heat generation as well, then you cannot use Fourier's law of conduction. You can only use Fourier's law under these assumptions. If these assumptions are not valid, you cannot use Fourier's law of conduction. So that is the reason that we have to come up with a generalized heat conduction equation. Generalized heat conduction equation. So Fourier's law was useful only to unidirectional. Unidirectional means temperature is a function of only x direction or y or z, whatever. Steady state means temperature is not a function of time and without internal heat generation. So only in this condition Fourier's law was valid. But if these conditions are happening, that means we have to come up with a generalized heat conduction equation. We cannot use Fourier's law. Okay. So how do heat generation take place? Heat generation can take place inside the body if there is a chemical reaction, or for example, you are supplying current or power. So if current is there, because of resistance in a conductor, heat generation can take place, or nuclear rods are there, so fission reactions are happening inside the body. Even that is also example of chemical reaction, but nuclear reaction is happening inside the body in a nuclear rod, so there can be heat generation. So that is why the whole objective of this study is first to define temperature distribution within the body. Okay, here we have assumed temperature is not changing with time, or it is only a function of x. Now if it is not happening, then how, what is the temperature distribution, how is it changing with x, with y, with z, with time? Okay, and also we need to make calculations for heat transfer, that is the objective for generalized heat conduction analysis. Okay, chalo, let's move on. Now first very, so we will do for all the three cases. What are the three cases? Cartesian coordinate, it is also called as rectangular coordinate, and then we will move on to cylindrical coordinate, then we will move on to spherical coordinate. Okay, chalo, let us start with Cartesian coordinate. Cartesian is basically in a plane slab. Okay, in a plane slab. So what is happening? Let us take a element, a very small element inside the body, of thickness dx, and x is changing in this direction. X is increasing in this direction. Okay. Now in this small element of thickness dx, what is happening? Some heat is entering q dot x and some heat is coming out. Okay, and there is some heat generation as well. Okay, so all the analysis or in thermodynamics or heat transfer starts with energy balance or energy conservation. Okay, energy is always conserved, it is a natural law. Okay, so for the element of thickness dx, we are only talking about this element, small element of thickness dx, energy balance we need to do. So let us do energy balance. What is energy balance? Energy balance, we can do whatever energy is coming in plus whatever energy is generated inside this element will be equal to energy that is going out plus energy that is stored. Okay, that is the energy balance. So what energy is going in? Energy that is going in q dot x, and some energy is generated as well, q dot generation. What is going out? Q dot x plus dx. X plus dx. Okay, whatever came in and whatever the small element has generated, that will change qx plus dx. And energy stored. So we always know any mass, if we have mass in the body, the mass stores energy in the form of internal energy, potential energy, and kinetic energy. Okay, in thermodynamics, you may have already heard that there are two forms of energy. Energy is stored and energy in transit. So energy stored is what? In terms of internal energy, potential energy, kinetic energy. Energy in transit is what? Work and heat. So energy is always stored in form of internal energy, kinetic and potential energy. But we can neglect the change in kinetic and potential energy. So the only thing that we have is internal energy. I will write a dot over that because it is change in internal energy. Change in internal energy. चलो ठीक है. Let us open this. Q dot x plus Q dot generation is equals to, how can I write this? Q dot x plus del y del x Q dot x dt by dx. ठीक है. Q dot x dx. One second. dx plus change in internal energy. Change in internal energy. Okay. Chalo. Let us simplify this. Let us simplify this. So I can directly cancel this. Okay. Now what can I write? I can write Q generation plus is equals to del upon del x minus k a dt by dx plus change in internal energy. Okay, so basically this, or you can also write this equation. I can actually write this equation. How? I can also write this equation as Q dot x plus Q dot generation minus Q dot x plus dx is equals to delta U dot. Dot means rate of change with respect to time. Okay. So now what is this called? This is the net heat interaction in an element. The net, this is what this portion is net heat interaction. And because of this net heat interaction, what is going to happen? The internal energy of the body will change. Okay, so net heat interaction is change in internal energy with respect to time. Okay, chalo. Now we all know how do you write delta U. How do you write? Can you tell me how do you write delta U? Change in internal energy. Can anyone tell me how do you write delta U? Delta U can be written as, tell me very quickly. Yes, very nice. MC dt. Very nice. Okay. Now I am not talking about delta U. I am talking about delta U dot. So I can write del by del T MC dt. Or I can also write MC change in temperature with respect to change in time. Okay, so I have to substitute this here. I have to not here. I mean, I can do it here as well, but our purpose is to put it here. Okay, wait. We are going to consider in the other direction. Just wait. Do not worry. Okay, chalo. We are only talking about x direction as of now. Okay, chalo. Now let us put it here. Okay, so this is the equation. This is the main equation. And from this equation, we have gotten Q dot generation is equal to, or I can say, yeah, is equals to minus del upon del x Q dot x dx plus what is u? mc dt by dx. Okay, the unit of this is watts. Okay, chalo. Let me simplify it further. Q dot generation is equals to, now let me write Q dot generation in terms of per unit volume. So I am writing Q dot generation into volume. The unit of this is watt per meter cube. Watt per meter cube. And this is again meter cube. So you will get it watts. Okay. Chalo. And that is del by del x. How can I write this? It is conduction qa dt by dx. Okay. Now how can I write mass? Mass flow rate. Mass is equals to density into volume, and volume is equals to A into dx. What is area? Area is this area, and thickness is this very small thickness, very small thickness. That is the volume, that is the dv. Okay, so let me write rho A dx del t by del x. Okay, now this volume is also area into dx. This volume is also area into dx. So let me write the final equation. Area into dx is equals to del upon del x minus ka dt by dx plus rho a dx dt by dx. Now what can I do? What can I do? Area, 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 dx, dx, dx. So what I am left with, if I rearrange this a little bit, I will get k d square t by, 1 second. I can write k d square t by dx square from here. And I have just taken it the other side. Okay. Plus heat generated is equals to rho mcp dt. I forgot C here. This C is also there. So C will come. C will come. And this is C dt by dx. Okay. Yes. No. Simple mathematics. Simple mathematics. Now let me rearrange this. Let me divide the whole equation by k. Let me divide this whole equation by k. So if I do that, I'll get del square t by del x square plus q dot generation. Always remember its unit is watt per meter cube. Watt per meter cube. Now if you divide it by conductivity, so here k will come below q dot generation is equals to rho c is also here, k will come here, and change in temperature with respect to time. With respect to time. This is what you are going to get. Okay. I can also write this as dx square plus q dot generation by k is equals to 1 upon alpha dt by d tau. And this is my general equation. If what is the condition of this? It is one dimensional. Why one dimensional? I am only talking about temperature as a function of x. It is unsteady state. It is unsteady state heat transfer. Why? Because temperature is a function of time. See the last term. See the last term, this term. And why it is valid? Why it is valid? With heat generation. Heat generation term is also there. Okay. Q dot generation is not equal to 0. Okay. Q dot generation is not equal to 0. Then you can use this equation. Then you can use this equation. Now what is alpha? Alpha is, can you tell me what is alpha? What is alpha? Can anyone tell me what is alpha? Alpha is thermal Very quickly. Yeah, no. Thermal diffusivity. Yes. Thermal diffusivity. K is thermal conductivity. K is thermal conductivity. Alpha is, so alpha is equals to K upon rho C. K is thermal conductivity. Rho is density. C is specific heat. Okay. What about units? Watt per meter Kelvin. Watt per meter Kelvin. Density is kg per meter cube. Specific heat is joule per kg Kelvin. Joule per kg Kelvin. Okay. So kg, in fact, let me write this watt into joule per second meter Kelvin. What I have wrote in joule per second. Okay. Then kg, wait. So what is in, let's say, joule per second, then meter and Kelvin is already there. Kg meter cube into joule per kg Kelvin. Now let us cancel. Let us cancel. Let's see the units. Joule and joule will cancelled. Okay. Kg and kg will cancel. Kelvin and Kelvin will get cancelled. And this meter cube will cancel this. And you will get meter square per second. So alpha is, we are going to talk about diffusivity. Do not worry. Okay. I am just telling you the only the mathematics behind it. Okay. Just the formula right now I am telling you. We are going to talk about what is the physical meaning of it. Okay, chalo. Now this is only valid under certain conditions. Under certain conditions. But what about if temperature is changing in y and z direction as well? So what will happen? Let us say heat. Let us say that, yeah, generalized heat conduction equation for x direction. X direction. What is that? D square t by dx square plus q dot generation by k is equals to 1 upon alpha dt by dx. This is for only for x direction, only for, but it is generalized. Why generalized? Because it is valid for unsteady state as well as for heat generation. So, but it is only for x direction. Now, the same thing that we have done, we will do for y and z direction. Similarly, we will repeat the same process for y and z direction. So, we will get this term for x direction. We will get this term for y direction. We will get this term for z direction. And we will also get this and this term, but it will be common. It will be common. There is no concept of it will come as common. Okay. 1 second. This is my mistake. What is my mistake? Nobody is telling me my mistake. You are not focusing. This is del t by tau. Okay. So this term and this term, these are not the function of x, y, and z. They are only a function of, they are independent of x, y, and z. So this will come as common, and you can take it out. And this is your generalized heat conduction equation. Now it is valid for three-dimensional heat transfer. Three-dimensional means temperature can change in x, y, or z direction. It is heat generation is also there. That means q generation is not equal to 0. And finally, unsteady state. Unsteady state, that means temperature is a function of time. So all, there is no assumption. I have taken no assumption. I am not assuming anything. It is the most generalized equation, but for Cartesian coordinate. Is it clear? Yes or no? Yes or no? Everyone, is it clear? Any doubt? Write in the comment box if you have any doubt. Chalo. Now, concept of thermal diffusivity. So as I have said, it is K upon rho Cp. K upon rho Cp, unit is meter square per second. Okay. So K also tells you how much heat can be conducted from one side to another side, one side to another side. Okay. If you have one body here, okay, and you maintain a higher temperature T1 here. Here it is T environment. But as heat is transferred from this direction to this direction, when you start feeling that surface is getting hotter, this will told you by, it will be told by thermal diffusivity. How fast or how slow you will start feeling the temperature on the other end, it will be told by thermal diffusivity. Conductivity will tell you how much heat will be transferred from one side to another side. Diffusivity will tell you how quickly, at what speed, how fast the heat will go from one side to another. So it is a thermophysical property of material. Okay. Thermal conductivity tells us how quickly the heat is diffused through the body. Okay, both the things are said by this diffusivity. I'll give you an example as well. The value of alpha talks about the ability of the material to allow rate of heat transfer to get diffused through it. Okay. Larger value of alpha means either K is large or small value of heat capacity. Okay. Now let us take an example. Okay. This is also, you can see alpha of gas is greater than liquid conductivity. This is okay. This you can read. Anyway, I'll take an example. So let's say you are drinking a coffee in a glass cup or in a ceramic cup. Right, usually we drink in a ceramic cup at home, right? Now tell me, I am telling you that thermal conductivity of glass is less is I'm sorry, is greater than thermal conductivity of no, one second. Thermal conductivity of glass is greater than thermal conductivity of ceramic. Okay. Glass already have very low thermal conductivity. Okay. So if I am saying thermal conductivity of glass is low, that means what? So you tell me, when you are holding a glass cup or a ceramic cup, which cup takes less time? In which cup you take less time and you start feeling hot or heat on the outer side? In which cup you start feeling heat on the outer side quickly, faster? Glass or ceramic? Which cup is more comfortable to hold? Which cup is more comfortable? You do not feel much heat on the other side. Tell me. You are holding a glass cup, you are holding a ceramic cup. Which cup is more comfortable to hold? You do not feel much heat on the outer side. I want answer from everyone. So ceramic cup is more comfortable. You know ceramic cup is more comfortable. But this is telling you that K, thermal conductivity of ceramic, is higher. That means what? That the heat should come out more quickly. Come out more quickly. But it is not happening. Why? Because rho of Cp of glass, is much less. It is much less than rho of Cp of ceramic. That means if that is less, that means it can hold, it is the storage capacity of heat. It can hold low, it can low or less heat inside the body. Inside the body, it cannot hold heat. It cannot hold heat. So whatever heat is coming inside from one end, it will allow it to pass to the other end more quickly. It cannot hold heat. But ceramic has higher heat capacity. It has higher heat capacity. So its conductivity is high. Yes, heat is coming in. But what is ceramic doing? It is absorbing the heat. It is not allowing it to go ahead. It is not allowing heat to go ahead. So on the other hand, on the outer hand where you are holding the cup, heat is diffused already from inside. Heat has come inside, but ceramic is storing that heat. It is not allowing to go on the other side. So that is why you will feel the hotness much later in the ceramic cup. Do you understand this? So up now see, alpha of glass is what? Look, this is also high. Like conductivity is high and this is low. This is low. That means or let us take alpha of ceramic as well. Ceramic as well. So this is already low and this is high. This means no denominator is high. So can I say alpha of glass is greater than alpha of ceramic? Can I say this? Yes, that is true. The ceramic, the material that ceramic is made of, it can store more and more and more heat. Look, heat is conducted. Heat has come inside because of conductivity. Okay, so heat has come inside, yes, but it is not allowing. It is storing the heat. It is storing the heat. It is not allowing the heat to go to the other side. Okay, because of this heat storage, and therefore conduct thermal diffusivity of glass is more. That means it is diffusing more and more heat, and that is why even though conductivity is less for glass, conductivity is less, but you will feel the hotness on the other end much quicker than ceramic. Okay, I'll give you another example. For example, there is an industry in which you are working. Okay, now one in that industry you have one normal this what do you call this cement wall. Okay, and you are touching that, you are just standing beside that ceramic wall, beside that cement wall. Okay, now you also have a steel wall and you go there and stand. So in and the work is happening inside the industry, you are standing on the outer side. So in which wall heat will be diffused faster, cement or steel wall? Yes, steel wall. Yes. Why? Because that cement has more heat storage. It can store more much heat. It will not allow, heat is conducted, yes, but it can store more and more heat. It is not allowing it to come other side. Conductivity is slightly different than diffusivity. Okay, although if conductivity is high, diffusivity will also be high, yes, but it is also possible that conductivity is high but diffusivity is low. Okay, for example, in the case of ceramic, what is happening? Conductivity is high, yes, than glass, but thermal diffusivity is low compared to the glass. Is it clear? Is the concept of thermal diffusivity clear? Because a lot of people remain confused between thermal conductivity and thermal diffusivity. Tell me, I want answer from everyone. Do you have any doubt? Do you want me to explain again, or like is it clear? It's clear. Very nice. Very nice. ओके, चलो एक बार और इसे थोड़ा सा कहीं से रीड करके देखना. ओके, बट द कॉन्सेप्ट इज दिस ओनली. ओके, Diffusivity means how long is it going to take to feel the heat on the other side. Okay, so if it is diffusivity is low, that means it will take more time for the heat to get diffused from one end to the other end. If the diffusivity is high, that means it will happen much quicker. You will feel the hotness outside much quicker. Okay, chalo. Now, so this was our general equation. This was our general equation. Okay, now let us make one assumption slowly, and we will then do, we will go ahead with that. Okay, so first is, let us assume that there is no internal heat generation. That means q dot generation will be equal to 0. So how can I write the above equation? I can write, I hope you already know that I can write this as, isn't it? I hope you already know this. Okay, so I can write del square T is equals to 1 upon alpha dt by d tau. This is called as diffusion equation. It is called as diffusion equation. Okay. Then steady state. Steady state means what? The temperature is not changing with time. Delta T by delta tau is equals to 0. So how can I write this? Now I can write plus q dot generation by k is equals to 0. Okay, and this is called as Poisson's equation. This is called as Poisson's equation. Okay, and finally, if steady state is also there, that means del T by del tau is equals to 0. And without heat generation means Q dot generation is equals to 0. Then it is called as, we all know it is called as Laplace equation. Laplace equation. Okay. Yes, very nice. That is Laplace equation. Sahil, very nice. Chalo. You will directly get these equations. Okay, you will directly get these equations. Okay, I'll wait for 1 minute. Chalo.
Uh, Hello, sir. Hello, sir.
Yes. Are you saying something?
Sir, I have one query, sir.
Yes.
Sir, in many of the books, when we referring alpha is equals to k upon rho c, so they will be always considering the value of Cp because
No. Sahil, you have to repeat. You have to repeat. I don't know. Your audio is not very clear. What are you saying?
sir, am I audible now? Is it better?
Yes. No, you are audible. Just some. So tell me. I'm listening.
Yes, sir. Sir, we have already derived the formula that thermal diffusivity is equals to k by rho
Upon.
c.
Yeah. Yeah.
But sir, usually it should be like rho Cp, right? Because if we take the example of the gases and other things,
Hmm.
the thermal conductivity varies significantly with the pressure.
Thermal conductivity. No thermal conductivity. You are talking about gases.
Yes, sir, about the gases.
No, thermal conductivity is not a very strong function of pressure. It is a strong function of temperature for gases.
So definitely, it's a strong function of temperature, but
Hmm.
it will also have a significant change with the high pressure
How are you saying it?
because of the thermal conductivity of the material. It completely depends upon its state and its function also. There, they consider
No,
temperature,
but
pressure,
yeah, I
structure.
mean, if we talk about, if we are talking about gases, right?
Yes,
So
sir.
temperature, basically, temperature also depends upon pressure. No, by PV is equals to MRT.
Right, sir. Definitely, that's what.
है ना?
Yeah.
हाँ, तो it is going to change up according to that only. If you're talking about pressure, but conductivity, we have a relation with temperature. We do not have a relation with pressure. Temperature,
No,
how
no,
it
sir.
varies? Ah, tell me.
No, sir. That's what. So, sir, that was the only query I had. But, sir, it's clear. It's clear. Yeah, I got your point, sir.
Okay,
I got your point. Yeah.
okay. Yeah, but I did not understand your question. I'm really sorry.
Sir,
Tell me one
actually,
more time.
what I was thinking that instead of writing the formula alpha is equals to k by rho c, we should write alpha upon k by rho cp.
Rho CP is basically CP and CV comes in only in the case of what? Tell me. CP and CV comes only in the case of
So the constant
gases.
pressure, constant volume, gases structure.
Yeah, only gases. No, for solids
Yes,
and
sir.
liquid, it does not matter, right?
Right.
Solids and liquid, Cp is equals to Cv, isn't it?
Okay. Yes. Okay. 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 I got your point, sir. I got
No,
your
so
point.
that is why
Yep.
we are writing C, because in solids and liquid, because we are talking about what, conduction, and conduction happens in solids. It happens in fluids and gases as well, but mostly we are talking about solids. Even if it is a fluid, okay, even if it is a liquid, but Cp is equals to Cv, so you can write just C, no problem. Only Cp Cv varies in the case of, it is different in the case
Yes,
of
sir.
gases.
Gases.
Okay,
Because of for solid and liquid, it's approximately equal. So there
it's
would
same
not be
only.
any change.
हाँ,
Yeah.
yes, 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 हाँ, ठीक है ना,
Okay.
clear?
Okay. I got your
That's
point, sir. Yeah.
okay, okay, चलो, let us move on. चले, आगे चले, चलो. So this is we are talking about steady state one dimensional heat conduction in Cartesian coordinate without heat generation. Without heat generation. Okay. It is steady state, one dimensional, and without heat generation. So for example, just to give you an example, heat transfer through your windows basically happens, is an example of this type of heat transfer. Okay. Inside the window, there is no heat generation, right? And also it is happening in only one direction, because this direction, x direction, for example, we are assuming this x direction is only significant compared to x, compared to the thickness of the glass. This z and y direction, y and z direction are much bigger. So whatever heat transfer is happening is insignificant. So we are going to assume that the heat transfer is only happening is, let's say you want to assume x, whatever you want to assume, you want to assume this as z, whatever you want to call this, but it is a function of only one dimension. If you want to call it z, it is okay. Okay. And steady state, because there is no heat generation, because there is no heat generation and only in one direction, and it is not changing with respect to time as well. Okay. So this is the case of steady state one dimensional in Cartesian coordinate without heat generation. Okay. So let us take this example. Let us take this case. Now we will be specific with our case. Okay, chalo. Steady state. Steady state. What do I call steady state? First, steady state means change with temperature with respect to time is equals to 0. Okay. Second, one dimensional means what? D square t by dy square is equals to d square t by dz square is equals to 0. It is not compulsory that you have to take d square t by dy square. Any two would be 0. I am taking that x is only happening. Okay. Any two could be 0, but it is only happening in one direction. It could be x, y, or z. Okay. Third, no heat generation. No heat generation. Q generation is equals to 0. So if I apply all these assumptions in the above equation, this is 0, this is 0, this is 0, this is 0. So what do I get? D square t by dx square is equals to 0. D square t is equals to dx square is equals to 0. Now this is my equation. It is only valid for what case? Under these assumptions, under these assumptions, under these assumptions. Okay. So is it clear? Chalo. So this is my equation. This is my temperature distribution equation. This is my temperature distribution equation. So this is my rectangular slab, isn't it? This is my rectangular slab. Now what is the boundary condition? X is changing in this direction. And I am assuming at x is equals to 0, t is equals to t1. At x is equals to L, t is equals to t2. And there is no heat generation. Of course, there is no heat generation. Okay, chalo. Now let me integrate this. Okay, so if I integrate the first time, I'll get dt by dx is equals to c1. Dt by dx is equals to c1. Okay, if I integrate this again one more time, I'll get c1 x plus c2. So this is how my temperature is changing with respect to x. Okay, I can anyway tell you that this is a linear equation. This is a linear equation, we all know. Okay, y is equals to ax plus b. This is a linear equation. Okay, but anyway, let us apply the boundary conditions. Boundary condition, let us apply. Let us apply the first boundary condition first. Okay, so let me apply first boundary condition. At x is equals to 0, t is equals to t1. So t is equals to t1, x is equals to 0 plus c2. What do I get from here? c2 is equals to t1. Okay, chalo. Let me apply the second boundary condition. So second boundary condition is when x is equals to L, t is equals to t2. So this will be t2, c1, L plus c2 I already know. Let me write c2 here, t1. Okay, so I have replaced c2 by t1. Okay, so t2 minus t1 by L is equals to c1. Is equals to c1. Okay, chalo. So I got c1. I got C2. Let me put this here. Okay. So what do I get? What do I get? T is equals to C1 is what? T2 minus T1 by L x plus T1. Now this equation is also telling me that it is a linear equation. So in a rectangular slab, in a plane slab, temperature variation is linear. How is the temperature variation? Linear. When all these conditions are satisfied. Steady state, one dimensional, without heat generation. In this case, temperature variation is linear with respect to x. In plane slab. In plane slab. Yes, one dimensional steady without heat generation. Temperature variation is linear. Okay, chalo, this is what. So how do I draw this? Anyway, we were drawing it like this, but now I know that this is varying linearly, like this only, like this. Okay, chalo. So this is my temperature variation. In this case is linear for plane slab when steady, one dimensional, and no heat generation, only then it is valid for plane slab. Okay, so it is linear. It is temperature distribution is not a function of k, so it is independent of material because k is a material property. Okay, so whatever the material is, temperature is going to linearly vary with x. Temperature is going to linearly vary with x. Chalo, very nice. Now we have come to steady state, one dimensional in Cartesian coordinate, yes, but with heat generation. There is a heat generation. Heat generation is not zero. Heat generation is not equal to zero. Okay, chalo, let us write this. So when I say steady state, that means dt is equals to d tau is equals to 0. One dimensional, when I am saying it is d square t upon dy square is equals to d square t by dz square is equals to 0. So what am I left with? This is 0. These two are 0. So I am left with d square t by dx square plus q dot generation by k is equals to 0. Look, I am going a little faster because these are derivations only. It is simple mathematics. Okay. If you have any doubt, just write it down. Stop me anytime in between. But it is simple mathematics. There is no concept that I can explain. It is simple mathematics. We are only working with a simple equation. Okay, I have derived an equation and I am working with this. Now let me tell you one more thing. Derivation is not important from gate point of view. Only results are important. Okay, but why I am doing the derivation? Because if I just give you the results, no, then you will not get feel of those results. Okay, so I am doing the derivation as much as possible. Anyway, I would need it to cover in one class. Okay, so if you get the derivation, if you want to do the derivation, it's well and good. For gate exam, derivation is not very important. लेकिन I'll tell you sometimes you have to derive it yourself. If the conditions are different, you need to derive it yourself. So very important that you need to know the derivation. Okay, but mostly you will get, because tomorrow we are going to do questions as well, but you will understand that derivation is not of very much importance in GATE exam. Okay, questions of today's session we will do tomorrow. So today is derivation. Okay, चलो, इसका मतलब ये नहीं है, that does not mean that your attention is divided. Okay, I need undivided attention. ठीक है, so this is my equation. When is this equation valid? Under these conditions. Under these conditions. Okay, so let us take this equation here. What is the equation? Steady state, one dimensional, with heat generation. Very important is with heat generation. Okay, so what is my equation? D square t by dx square plus q dot generation by k. Okay, anyway, let me write it small k. Okay, whatever is written earlier, forget it. It is small k because its unit is watt per meter cube. Okay, chalo, it is equals to 0. Okay, now can I write it as d square t by dx square is equals to minus q dot generation by k. Now let us integrate. What will I get? dt by dx is equals to minus q dot generation by k x plus c1. Very nice. Let us integrate one more time. Temperature is equals to minus q dot generation x square by 2 plus c1x plus c2. So this is my temperature distribution equation. What equation? Like the equation we got here. Which equation? This equation. Okay, so it is the same thing. Now we have two constants here, c1 and c2. In order to find out c1 and c2, I need to apply some boundary condition. What are the boundary condition? So let us take the case of thermal symmetry. First case is thermal symmetry. What do you mean by thermal symmetry? Look, heat is entering, heat is going out, whatever is happening, heat is generated. But thermal symmetry means whatever is happening inside the body, I need the same temperature on either ends. On both the sides, I need temperature same, which is TW. Okay, so let us assume that here at midpoint x is equals to 0. On either end, it is x is equals to minus L and plus L. Okay, so what is the boundary condition? Boundary condition is at x is equals to plus minus L, temperature is equals to TW. Okay, now do not assume that this is the only case. There is a case of thermal unsymmetry as well, where the temperature could be different. Okay, then you need to derive it again, but we are deriving for thermal symmetry. Okay, chalo, you need to know the steps. But if the another case comes, then you need to derive it yourself. Okay, but it will be for GATE exam, it will be a very small derivation. Now temperature, I defined temperature distribution equation. This equation is what? Minus q dot generation by k 2k x square plus c1x plus c2. Okay, now let me apply first boundary condition. What is first boundary condition? X is equals to minus L, T is equals to TW. Okay, so what will I get? I will get TW is equals to minus q dot generation by 2k. Here we have minus L square plus C1 minus L plus C2. Okay, so can I write it as minus q dot generation by 2k L square, because it is minus L square. So minus square means plus, minus C1L plus C2. Okay, Second boundary condition. What is second boundary condition? X is equals to plus L, T is equals to TW. Let me apply this. TW is equals to minus Q dot generation 2K L square plus C1L plus C2. Okay, what can I do now? Let me add them. So 2TW is equals to 2 minus one second. Okay, 2TW minus 2 Q dot generation upon 2K L square. 2K L square. अब देखो, this will get cancelled. This will, it is minus C1L plus C1L to, and this is 2C2. 2C2. Okay, so from here I can get C2 is equals to TW, because this 2 will also get cancelled. Okay, TW plus Q dot generation by 2K L square. This is my C2. Now let me put C2 here. So when I put C2 here, what will I get? Let me write this on the next page. I can't write it here. TW is equals to minus Q dot generation by 2K L square. Okay. Plus C1L plus TW plus Q dot generation by 2K L square. Okay. Yes, very nice. Very nice. Chalo. So TW and TW get cancelled. Same sign. This is opposite sign. This will get cancelled. And you will get C1L is equals to 0. That means C1 is equals to 0. Okay. Now I got the value of C2 is this. C1 is 0. That is what I wanted to do. Now I can substitute in this equation. What will I get? This is the general equation now. T is equals to minus Q dot generation 2K X square plus TW plus Q dot generation. You know C1 is 0. So C1 I can remove. Generation by K L square by 2. This is my general equation. This is my temperature general equation. Okay. Now I need to find out. You see, this is by 1 second. Okay. This is my body. Now what I am saying here, it is TW. Here also it is TW. And there is heat generation inside the body. Now that means there is a location. There could be a X. If X is decreasing in this direction, increasing in this direction. So there will be a location at which X will be maximum. I need to find out that location. How will I find out that? I'll do dt by, let me write it, to find out location, that means X, for maximum temperature. What will I do? dt by dx is equals to 0. So dt by dx is equals to what? By, we will only get this, what? Q dot generation 2K into 2x. TW is also not a function of x, and this is also not a function of x. So plus 0, and I need to put this is equals to 0. That means if you solve this, x is equals to 0. That means at x is equals to 0, t is equals to t maximum is equals to t naught. Okay. Now, how do I find out T maximum? How do I find out T maximum? Put x is equals to 0 in this equation. So now what can I apply? At x is equals to 0, T is equals to T naught. So T naught is equals to 0 plus TW plus Q dot generation. I know that today's class is getting boring, but I cannot do anything about it. Okay. If you want, I can skip the derivation and tell you the results. Look, that is the compromise that you need to do. Okay. Chalo. So T naught, how much is T naught? T naught is equals to this. T naught is equals to this. This is your maximum. This is your maximum temperature. Now, so what do I get here? What do I get here? Maximum temperature is equals to TW plus Q dot generation 2K L square. Okay, so can I write it here? TW minus T naught is equals to minus Q dot generation by 2K L square. I can write this? Yes? Now, so now what else do I know? Look, I know this as well. What? Temperature equation, temperature equation. Okay, where is this? So this is your first equation. Okay, now I have this equation as well. T minus TW, this equation. Okay, I can take a, let me rewrite this equation. There's so many equations. T is equals to minus Q dot generation by 2K L is, what is this? X square plus TW and plus Q dot generation 2K upon 2K into L square. Okay. So can I write T minus TW is equals to Q dot generation by 2K L square minus X square. Is it clear? Is it clear till now? Is it clear till now? Okay. Chalo. So now what is TW? TW is, you can take it out TW from here. Okay. So let me write it. TW is equals to T naught. 1 second. Plus it is minus T naught plus Q dot generation by 2K L square. Okay, from here I have taken out TW and this is already there. Just 1 second. Okay, so Q dot generation, always remember the unit is watt per meter cube of this. Okay, so if I solve this, I'll take this on the other side. I'll take the other side and I'll take this common. I will get T minus T naught is equals to Q dot generation 2K X square, because L square minus L square will get cancelled. L square minus L square will get cancelled. So now I have this equation. Okay, so it is TW T minus T naught is equals to Q dot generation by 2K X square upon TW minus T naught upon Q dot generation by 2K L square. So this and this will get cancelled. You will get X by L ka whole square. Now this is your temperature distribution in the case of heat generation. In the case of heat, which negative sign? Which negative sign? This will come on the other side. No. TW, here we have minus. So it will become positive, right? Are you telling about this sign?
No, sir, like we are taking Q generation to the other side, right? So, like when we minus the x.
Okay, wait. Tell me. Hello?
Hello, sir. Hello?
Tell me.
Like when we take Q gen L square by 2k to the other side, there we will cancel out the L square and minus x square will be left out, right?
Yes.
So
Okay. There is a minus
Q.
sign here. Yes. Okay. So here we already have some minus and it will get cancelled. Is it okay? Okay. ठीक है. Chalo. So now why this equation is important? For example, you know the maximum heat, maximum temperature in the body, you know. Okay. And T wall is also given to you. So you can find out the temperature at any x. With this equation, you can find out temperature at any x by using this equation. Particularly in this case, remember, you cannot use this equation without this. You cannot use this equation without these assumptions. Okay. So what is this equation? This is a parabolic equation. This is a parabolic equation. Okay. Chalo. So this was my general equation. Now, when I took steady state, one second. One dimensional, and with heat generation, this is my temperature distribution equation. You see, we have derived this. We have derived this equation. Where have we derived? This equation. This equation we have derived. Okay. This equation we have derived here. Chalo. Now we applied the boundary condition. What was the boundary condition? X is equals to plus minus L. T is equals to TW. On the both sides, we have the same temperature. It is called as thermal symmetry. Okay. So we have derived that this is the temperature distribution, and temperature distribution, it is very important. The objective questions will directly ask in this particular condition, what is the temperature distribution? Parabolic, hyperbolic, linear, okay, logarithmic. Directly they will ask. Temperature distribution is parabolic. Okay, it is parabolic. Now, so what happens if there is not thermal symmetry? Okay, this is non-symmetry. So we have this side we have T1, this side we have T2. What will you do? Look, your temperature distribution equation will remain same. Now you will put these boundary condition in this and find out C1 and C2. Once you have found out C1 and C2, you can put that back here, and then you will get a temperature distribution equation as a function of x. That you will know how the temperature is varying in this particular case. And then what you can do? You can do dt by dx. You can put that equal to 0 to find out x max. At what location you are getting the maximum temperature. Okay. So these T1 and T2 will be given to you in question, and you can put this and solve. Okay. Is it clear? Is it clear to everyone? Shruti, any doubt? Chalo, theek hai. Look, I am very happy to skip derivations. I have no problem. Okay, but if I just give you whatever I am going to do that anyway for spherical, I am going to directly tell you the results. But in the initial level, I think it's good idea to know how we are proceeding. So if in exam, if they slightly move out of the the conditions, because everything we are doing, we are applying some boundary conditions, we are applying some assumptions, then only we are doing it. Okay, so if you know the process, you can apply them. Okay, chalo, let us move on. Now we have come to cylindrical coordinate. Now we have come to cylindrical coordinates. Okay, so cylindrical coordinates, what we are going to do, we are going to apply with the same energy conservation. We have applied this. Okay, we have applied this. Now what we are going to do, we are going to derive it for, we are, first of all, we are only talking about thickness dr. Then we are going to extend this later on. We are going to extend this later on. Okay, chalo, theek hai. Let me extend. This is the same equation which we have taken, energy balance. Okay, chalo. Now if I extend this, it is q dot x plus q dot generation minus q dot x minus del upon del x q dot x dx is equals to m c dt by d tau. Okay, now this I can conveniently cancel, no problem. This I can conveniently cancel. How can I write this in the form of, look, this is watts, but I'll write this in the form of watt per meter cube. So I'll have to multiply it by volume. Volume is area into dr, area into dr, small dr. Okay, just 1 second, slightly mistake I have done here. Okay, slight mistake I have done here because I have taken the same equation dx. 1 second. I have taken the general equation of Cartesian coordinate. It is my mistake. Chalo. I'll do this as q dot r plus q dot generation minus q dot r minus del by del r q dot r dr is equals to mc dt by d tau. No problem. Chalo. This will be get cancelled. I can write this q dot generation a dot dr minus del upon del r minus ka dt by dr is equals to, again, mass, density into volume, density area into dx into c dt by d tau. Okay, now look, I cannot cancel this area because this area is a function of r. Okay, and r is coming under this, so I cannot cancel this directly. Okay, but I can divide everything by area. I can divide everything by area into dr. So dr will get cancelled, and it will become as q dot generation minus, if I cancel this area and this area, then I need to divide this by area. Okay, so what is area? 1 upon 2 pi rl. Okay, then del upon del r minus k 2 pi rl dt by dr is equals to rho c delta t by delta tau. Okay, so this minus, now 2 pi and L can be cancelled. 2 pi and L, because they are constant. Length will remain constant. Heat transfer is only happening in the radial direction, so length will remain same. This is not a function of length. Okay, so what we will get here, I can write, look, this plus minus, 1 second. I can write 1 by r, this r, del upon del r minus k, not minus k, now minus minus ho gaya plus. Okay, so this minus came out and this is plus. dt by dr plus q generation is equals to rho c dt by d tau. Clear? Is it clear till now? Okay. Now what can I do? Let me divide everything by k. So if I divide everything by k, this will gone out because conductivity is constant. Okay. This will be divided by k. This will be divided by k. Okay. So what we got eventually, we will got 1 by r del upon del r minus r dt by dr plus q dot generation by k is equals to 1 upon alpha dt by dt. Now I don't think I need to tell you about alpha, k upon cp, rho c, k upon rho c, k upon rho c. Okay. Yes, very nice, very nice, very nice. Sorry, my mistake. चलो ठीक है, तो ये हो गया. Now this is my generalized equation for cylindrical coordinate. I am talking about cylindrical coordinate, which means it is one dimensional. What dimensional? Temperature is a function of r, and unsteady state, unsteady means temperature is a function of time, and heat generation, heat generation is happening means q dot generation is not equal to 0. Then only, and it is for cylindrical coordinate, then you can use this equation. This is general equation. Okay, chalo. Now what will happen if I am not talking about just r direction? So I am going to consider that for r, theta and z, r, theta and z. So there is a whole derivation for it, which is really of no use for us. Seriously. Okay. So for r direction, what we have defined, 1 upon r del upon del r dt by dr. You have to write this equation so many times that you yourself remember it as it is. Okay, you don't have to see it back again and again, although I need to sometimes see this again and again, but because I am not preparing for it, you are preparing. Okay, so I can have the leverage of taking go back and see, but you don't have the leverage, you don't have the freedom, leverage that I have. Okay, I have done my part. Chalo, theek hai. This is for r direction. Now similarly, if you do the same for phi and z direction, so you will get this equation. This is your generalized heat conduction equation in cylindrical coordinate. It is three-dimensional, means temperature is a function of r, phi and z. It is unsteady state, means temperature is a function of time, and it is heat generation. For all the conditions it is valid. Q dot generation is not equal to 0. Okay, clear? Is it clear? Everyone, I want answer from everyone. Is it clear? I know it is simple mathematics, but I can't do anything about it. I'm really sorry. Chalo, theek hai. Just let me drink one sip of water. Chalo. Now we need to do the same thing. We can't do anything else. Okay. So this is my general equation. Now I'll take the most simplest case. What? Steady state. One dimensional and without heat generation. So without heat generation means this is 0. Steady state means this is 0. And one dimensional means this and this both are 0. So I can write 1 upon r del upon del r dt by dr is equals to 0. Is equals to 0. Okay, this is my equation under these conditions. Under these conditions, steady state, one dimensional and without heat generation. Without heat generation. Okay. So can I write it like this, del upon del r? R dt by dr is equals to 0, because r will go that side and it is equals to 0. Okay. Now let me integrate it one time. Integrate it first time. So what will you get? R dt by dr is equals to C1. Very simple. Integrate it one more time. Integrate it one more time. Okay, we will integrate again later on. But let me simplify it. Is equals to C1 by R. C1 by R. Okay. Now if I integrate it, I'll get T is equals to C1 ln R plus C2. Oh, so what do I know? In the plane slab, under these conditions, the temperature distribution was linear. But under these conditions, for a cylindrical coordinate, the temperature distribution is logarithmic. It is logarithmic. Okay, chalo. But I can't leave it here. I can't leave it here. I need to simplify it a little further. Okay. So what do I get here? I have already derived it that the temperature distribution is C1 ln R plus C2. C1 ln R plus C2. Okay. Now I have to apply the boundary conditions. I have to apply the boundary conditions. Okay. So what are the boundary conditions? If this is the cylinder, okay, at the inner surface, temperature is T1. At the outer surface, at R is equals to R2, temperature is T2. So it looks like this. At R is equals to R1, temperature is T1. At R is equals to R2, temperature is equals to T2. So these are my boundary conditions. It's very simple. It's very simple. You can do it yourself as well, because I am not doing it. Actually, I don't know if I left the space. I have not left the space as well, but it's very simple. Okay, it's not a very big issue. You or for gate also it is not required, but it is a simple step. What are simple step? Look, you apply these boundary conditions. You apply boundary conditions. Calculate. Apply boundary conditions and calculate C1 and C2. Okay, C1 and C2 we have calculated. Then substitute C1 and C2 in temperature distribution equation. Which equation? Again, this is the temperature distribution equation. Temperature distribution equation. Okay, so once you do that, you simplify that and you will find out this equation. You will find out this equation. Also, what else you can do? Temperature distribution, once you substitute this, then you find out to locate R for maximum temperature T naught or T maximum. You differentiate it with respect to R, put is equals to 0. Okay, and you will find out at what R temperature is maximum, and anyway, okay, you will find out it is at the center, because anyway temperature is going, heat is transferred from inside to outside. Okay, and it is going in the radial direction. That simply means that at R is equals to 0, at the center point, temperature will be maximum. Temperature will be maximum. Okay, because as you are going up, your temperature is, as you are going far away from the center point, temperature is reducing, heat is getting transferred. Okay, chalo. So what do I know? What do I know? What is the temperature distribution? It is logarithmic. It is logarithmic. For cylinder, temperature distribution is logarithmic under these conditions only. Okay, it's very important that you follow. First of all, you ensure that these are your conditions, then only you will be able to use this equation. If the case is for unsteady, you cannot use this equation. If the case is for with heat generation, you cannot use this equation. So it's very important. Okay, now temperature at any point in the cylinder can be expressed as the function of radius only. As a function of radius only. Okay, so if you know T1, if T1 and T2 is given to you, Okay, and R1 and R2 is also known to you. Then by using this, you can find out temperature at any radius. At any radius. Okay, clear? Chalo, chalo. Next is with heat generation. With heat generation. Now we are going to talk about with heat generation. Okay, ठीक है. Steady state means this is zero. Now let me tell you one more thing. Today we have talked only for steady state. Unsteady state we will take a completely different session. Okay. Tomorrow is numerical session. Then we will move to fins. Then we will move to fins. Okay. Then we will move to fins, and then let me tell you one more time. Tomorrow is numerical question session for all the thing that I have done till now. Okay. Then, although we have already covered so many numericals in the last class as well, then we have fins next class. Then we have unsteady state. Okay, so 3 classes are like this only. Okay. Then we will move to heat exchangers, radiation, and all these things. Convection. Okay. Chalo. Now the next case is steady state one-dimensional heat conduction in cylindrical coordinate system with heat generation. Now heat is getting generated. Heat is generated inside the body, inside the element. So but it is saying steady state. That means this is zero. It is saying one-dimensional means this and this is zero. So what do I get? 1 upon r del r dt by dr is equals to minus q dot generation by k. Okay, this is small q. Always remember the units. In question, you have to see what is the units, and then you have to what do you say? You have to unify the units. Okay, you have to see that if I am using the correct units. Okay, q dot generation. Okay, now what will I do? Can I write it like this? Del upon del r. 1 second. Let me use black. Okay, del upon del r dt by dr is equals to minus q dot generation by k into r. This r has gone on the other side. Okay, now let's integrate. Simple integration is simple in this case. Is equals to q dot generation by k r square by 2. Very simple. Now can I write it like this? dt by dr is equals to minus q dot generation by k by 2k into r, because this r will cancel this r. Okay, now let me integrate one more time. So it will be temperature is equal, 1 second, it is plus c1 as well. I forgot the integration constant. Okay, chalo. Q dot generation by 2k r square by 2 plus c1. Okay, just 1 second. There is little. Okay, let us start from here one more time. Little bit, there's no big issue. Just I forgot the r. So, okay. If I integrate, what will I get? I will get r dt by dr is equals to minus q dot generation by k, and this is r square by 2 plus c1, integration constant. Yes. Okay. Now, if I further solve it, I can write dt by dr is equals to minus q dot generation by k 2kr plus c1 by r. Very nice. Chalo. Now let us integrate one more time. So I will get t is equals to minus q dot generation by 2k r square by 2 plus c1 ln r plus c2. So ultimately, the equation, the temperature distribution equation, I get with heat generation is minus Q dot generation by 4K R square plus C1 ln R plus C2. This is my temperature distribution equation. This is my temperature distribution equation. Chalo. Now, okay, anyway, I don't need this. Let us move here. So this is what I get. This is my temperature distribution equation. And this is dt by dr that I calculated earlier. Okay. This is my dt by dr. Okay. Now, so let's talk about thermal symmetry. What is thermal symmetry? At R is equals to capital R, T is equals to TW. I don't need this boundary condition anyway. Okay. T is equals to TW. Okay. So thermal symmetry is that all over the surface, all the boundary temperature will be TW everywhere. Okay. So what do I do? I can put, first of all, what can I do? I can put this boundary condition in both the equation. First of all, what do I do? Let us say dt by dr at R is equals to capital R. Okay. So is equals to minus Q dot generation by K capital R. Okay. Capital R 2 plus C1 by R. That is your equation A. Now, in order to maintain steady state, if you have to maintain the steady state, whatever heat is generated inside the body, you have to convect it outside. If this is your cylinder, whatever is generated here at the center, it needs to be convected out by using some fluid. Only then you will be able to maintain constant temperature on the boundaries. That is the main criteria for nuclear rods. You have to maintain whatever chemical reactions are happening inside, whatever heat is getting generated, but you need to maintain a constant temperature outside the nuclear rods, because you cannot let the temperature of nuclear reaction and nuclear rod increase. Otherwise, there will be uncontrolled reaction. So you cannot allow that. Okay. So in order to maintain a steady state, whatever heat is generated, Q dot generated into volume is equals to Q convected. Whatever heat is generated, you need to take it away by using convection. So what can I write? Q dot generated volume is pi r square L is equals to, it is first of all conducted. Okay. So it is conducted out of the nuclear rod. You see here, first of all, it will be conducted out and then it will be convected out. Okay. So it is also equal to conduction and then it will be equal to convected. Okay. Now it is minus Ka dt by dr at R is equals to capital R. Okay. Only here it will be equal to Q convected. Okay. Where is Q convective happening? At the surface at R is equals to capital R. Here. Okay. Is it clear till now or not? Any confusion in here? Convection is happening at outer radius at R is equals to capital R. Is it clear? Any doubt till now? Then we'll move ahead. Chalo. So area is how much? Area is pi r square L is equals to minus K 2 pi capital R L dt by dr at r is equals to capital R. Okay, so pi and pi will get cancelled. 1 r, L get cancelled. So dt by dr at r is equals to this is equals to, it is my mistake. What is my mistake? That I have replaced this by q dot generation, capital Q. Okay, these equations were written and I copied it like this only, but it is small q. Whenever I am using it like this, it is small q. Okay, look, capital Q dot generated, its unit is watt, but small q generated is equals to watt per meter cube. So there is a mistake, kindly ignore it. And q dot generation is equals to q dot generation into volume. Okay, actually I had this equation, I had written it somewhere, so I directly copied it. So that is why it is written like this. Okay, chalo. Now, so if I simplify it, I'll get q dot generation, एक r, we have this r upon minus is there and 2k. Okay, so this is your equation B. Now if you compare A and B, both are telling you dt by dr at r is equals to r. Now if you compare this, if I am saying both are same, so when these both can be same? Only by equating A and B, I can say that C1 is equals to 0. C1 is equals to 0. So in this case, we have got C1 is equals to 0. Okay. Now what can I do? I need to find out location of maximum temperature. So I need to find out R, that will give me maximum temperature. So how do I find out? I have this equation, dt by dr. Okay. So dt by dr is equals to minus q dot generation by 2k r plus c1 by r. Okay, plus c1 by r. And I know that c1, I have just now find out that c1 is 0, then it is equals to 0, and we need to put it is equals to 0. And what is it giving me? What is it giving me? That what is the location of maximum temperature? What is the location for maximum temperature? So minus q dot generation into r by 2k is equals to 0. That means that r is equals to 0. It is the location of T max or T naught. T max or T naught. Okay. So now what do I do? Let me put this here. Okay. So this is my equation. What is the equation? T is equals to minus q dot generation by 4k r square plus c1 ln r plus c2. Okay, this is my general equation. Now I know that at r is equals to 0, T is equals to T naught, yeah, T max, maximum temperature. Okay, so if I apply this, T naught, R 0, so that means that is 0, plus C1 is equals to 0, plus C2, that means C2 is equals to T naught or T maximum. That is what you have to do every time. Every time you get these conditions, you go to the basic equation, you apply the boundary condition, you find out C1 and C2 and equate in the main equation. So what is the main equation now? T is equals to minus q dot generation by 4k r square. Now C1 is 0, so I will not write C1, plus T naught, Okay, so can I write T minus T naught is equals to minus q dot generation 4k r square. Yes, I can write this. Okay, and I also know that at r is equals to capital R, t is equals to tw, t is equals to tw. That is also I can put in the same equation. So I get what? Tw minus t naught is equals to minus q dot generation by 4k, and it is capital R square. So this is two equations. Okay, now I can just compare these two equations. I can compare these two equations. What? T minus T naught is equals to minus Q dot generation by 4K R square upon TW minus T naught minus Q dot generation 4K capital R square. So this and this will get cancelled. T minus T naught upon TW minus T naught is equals to R by R square. So what is this equation? Again parabolic. Do you remember the last equation of Cartesian coordinate? T minus T naught, TW minus T naught is equals to x by L ka whole square. This is what? Rectangular coordinate or Cartesian coordinate. When steady state is there, one dimensional is there, but with heat generation. And this is for cylindrical coordinate. This is also parabolic. This is also parabolic. Okay, clear? Chalo. When you are trying to say something, please write it before in the comment box. Why? Because I do not have earphones in my ear. Okay, so I can't hear you what you are saying. I'm only seeing the comments. So by chance, if I'm looking at the screen and you are speaking, then only I will know. Otherwise, write in the comments if you are saying something. Okay, chalo. Now the final. Okay, this is what we have done with heat generation. If I am talking about, this is my temperature distribution equation. I have applied the boundary condition at R is equals to capital R, T is equals to TW, and I have find out C1 and C2, and this is my parabolic temperature distribution. Okay, chalo. Finally, let us come to spherical coordinate. No, I don't remember any time this question came. Look, in the last 6-7 years, I don't remember if any question came from this. And anyway, spherical coordinates are very rare. On critical thickness and all will come, but not on generalized heat conduction equation. So it is not very important. Still, let us try to take a brief idea of this. Okay. So again, spherical coordinates are r, phi, and theta. Okay. And we will start from this equation. And this is my generalized equation. This is my generalized equation. Okay. This is my generalized equation. Now, it is in R, it is three-dimensional, unsteady state, and finally with heat generation. With heat generation. Okay. Now, if I consider the same case, steady state, one dimensional, without heat generation, तो भैया steady state, one dimensional, and no heat generation. So what will I get? 1 upon r square del upon del r square del t by del r is equals to 0. Okay, so if I simplify it, what will I get? Del by del r square plus dt by dr is equals to 0. Okay, now let us integrate. Let us integrate. You will get r square. It is dot. Okay, dt by dr is equals to c1 is equals to c1. Okay, now can I write dt by dr is equals to c1 by r square. c1 by r square. So let us integrate one more time, because we need temperature distribution equation, right? If you integrate this, you will get T is equals to C1. Now, what is the integration of 1 upon x square? 1 upon x square. It is minus 1 upon x. It will go up. It will go up, right? Integration of x to the power minus 2. I hope you all know this, right? X minus 2 plus 1 minus 2 plus 1. And it is minus 1 by x. Okay, chalo. So this is minus 1 upon r plus C2 plus C2. So what is the temperature distribution eventually? So from this, the temperature distribution is minus C1 by r plus C2. This is your temperature distribution equation. This is your temperature distribution equation. Now same. Okay, so I have already derived it for you, and you have gotten T is equals to minus C1 by R plus C2. Temperature distribution. This is your temperature distribution. Okay. Now again you are going to apply the same boundary conditions for a sphere. We all know, look, this is your hollow sphere. Okay. At R is equals to R1, T is equals to T1, at R is equals to R2, T is equals to T2. Okay, so when you again do the same thing, okay, you apply the boundary condition, calculate C1 and C2, put C1 and C2 here again, and you will get a generalized generalized temperature distribution equation. Okay, and the steps will be followed, and you will get this temperature distribution equation. What is this equation? What is this equation? It is hyperbola. It is hyperbola. Okay, so temperature at any point in the cylinder can be expressed as a function of radius only. Similarly, for cylinder, it can be expressed as radius only. Okay, and the final case now with heat generation for spherical coordinate with heat generation. Okay, so steady state means this is 0. One dimensional means this, and this is 0. So this is your equation. This is your equation. Okay. Again, what can you do? You can simplify it as del by del r square dt by dr is equals to minus q dot generation by k into r square into r square. Okay. Okay. ठीक है, अगर थोड़ा जल्दी कर लोगे तो मैं एक बार समरी करवा दूंगा यार, इसलिए मैं कह रहा हूं, पता है, क्योंकि इतना स्केटर्ड हो गया है ना, तो मैं एक समरी अगर करवा दूंगा तो थोड़ा आइडिया हो जाएगा आप लोगों को। चलो 10-5 मिनट लगा के आई विल गेट अ समरी। ठीक है, चलो ये हो गया। नाउ यू हैव टू इंटीग्रेट दिस। सो व्हेन यू इंटीग्रेट दिस you will get r square dt by dr is equals to minus q dot generation by k r cube by 3 plus c1. Okay, now if I simplify this, I'll get minus q dot generation by 3k, then again r will come here because it will be divided by r square plus c1 by r square, c1 by r square. Now again integrate. So you will get T is equals to minus q dot generation by 6k r square minus C1 by R, because again you are going to integrate this, it is minus C1 by R, okay, plus C2. So this is your temperature distribution equation for spherical coordinate with heat generation, okay. So this is your equation. You apply the boundary conditions, okay, at x is equals to 0, dt by dr is equals to 0, and again you can do the same thing what we did in cylinder, okay. You actually start with this equation, okay, you put this here, and then whatever q is generated, it will be conducted or convected. So you can apply that formula and you can find out a temperature distribution equation. Whatever you will get, it will again come. What was earlier equation? Logarithmic pole. Tell me very quickly, what was the earlier equation for heat generation? Logarithmic, exponential, hyperbola. With heat generation, shown. Parabolic, very nice, parabolic. So this will also come as parabolic, okay. Chalo. Now, without wasting any time, let us revise what we have done today so that you will get some clarity, okay. So we will start with Cartesian coordinate. We will start with Cartesian coordinate. Okay, Cartesian coordinate. So first of all, we defined a general equation. I know for Cartesian, so I am going to write it. Then I don't know for the rest of them. I am not going to write this. Okay, this is your general equation. Okay, now what did I do? Steady state, one dimensional, without heat generation, Okay, so the equation came as d square t by dx square is equals to 0. And then I applied boundary conditions as x is equals to 0, t is equals to t1, x is equals to L, t is equals to t2. And you get from here t is equals to, 1 second, here you will get t as a function of x, c1x plus c2. That is a linear equation. Okay, so it is linear. Okay, so you need to understand under this case temperature is varying linearly. You can also remember that equation, t is equals to t2 minus t1 by L x plus C2 was how much, T1 or T2? I think it was T1. I don't remember it correctly, but I think it is T1. Yeah, it is T1. Yes, sorry. Chalo. Okay, so this is your linear equation. It's very important that you remember that how the temperature is varying, Now, second case, what was the second case? Steady state, one dimensional, with heat generation. Okay, so what was the equation? Equation was d square t by dx square plus q dot generation by k is equals to 0. Okay, this is the equation. What did I do? Boundary conditions. X is equals to plus minus L, T is equals to TW. It is thermal symmetry. symmetry. There could be a case of thermal non-symmetry as well. So you have to do the derivation yourself. Okay, agar it is different than this, you have to do the derivation yourself. Now, what is the temperature distribution equation? Temperature is changing as minus q dot generation by 2k x square. Let me know if it is wrong, if you are writing it already, because I am just guessing. Okay, chalo. Now, so what is the final equation that you got? Temperature distribution T minus T naught upon TW minus T naught x by L whole square, and this is parabolic. This is about Cartesian coordinate. Okay. Next, cylindrical coordinate. Cylindrical coordinate. What did we do in cylindrical coordinate? Okay, I don't actually remember the whole equation, so I am not going to write it anyway. I'm not writing the whole equation. I just remember the R part. Okay, so that I am going to write. Okay, so first case, steady state, one dimensional, without heat generation. There is no heat generation. So equation was 1 upon R del upon del R dt by dr is equals to 0. I hope this is right. Okay. Then we applied boundary condition. What are the boundary conditions? At R is equals to R1, T is equals to T1, at R is equals to R2, T is equals to T2. Okay. By doing this, what did we get? T is equals to C1 ln R plus C2. This is what we got. And when we calculated the temperature distribution T minus T1, 1 second, upon T2 minus T1 is equals to ln R by R1 upon ln R2 by R1, and this is telling me that it is logarithmic. Okay, it is logarithmic. Okay, so in this case the temperature distribution is logarithmic. Okay, next second case, steady state, one dimensional, with heat generation. Okay, so what is there? 1 upon R del upon del R dt by dr is equals to minus q dot generation by k. This is my equation. Now I have applied boundary condition. What is boundary condition? Thermal symmetry. R is equals to capital R, T is equals to TW. Okay, T is equals to TW. And the temperature distribution equation that I will get here is minus q dot generation upon 4k R square plus C1 ln R plus C. This was my temperature distribution equation, and I have derived T minus T naught, TW minus T naught is equals to R by R square. And again, that is parabolic. Yes, very nice. Sean, very nice. This is cylindrical coordinate. Next is spherical coordinate. Finally, last is spherical coordinate. Okay, chalo. First case, again I don't remember the whole equation. It is steady state, one dimensional, and without heat generation. Okay, now, so what is the equation? 1 upon R square delta by del R r square dt by dr is equals to 0. This is my general equation in this case. Temperature, I applied boundary condition. What are the boundary condition I applied? Same what we applied for cylinder. T is equals to T1, R is equals to R2, T is equals to T2. When I applied this, I got temperature is equals to minus C1 by R plus C2. And finally, the temperature distribution is this one. And this is hyperbola. Hyperbola. Yes, very nice. And finally, the last case is steady state, one dimensional with heat generation. So what was the equation? Simple. You will add heat generation here. 1 upon r square del upon del r. At least itni to you have to remember these many equations. You can't skip these equations. Okay. इतना तो आपको करना पड़ेगा. इससे if you are not trying to remember more than this, it's fine. Okay. You don't need to remember the whole equation. No need. There is no need of that. Okay. Chalo. This is your equation. Again, you have applied boundary condition at r is equals to capital R, T is equals to TW. And the temperature distribution you will get here is minus Q dot generation upon K 6K R square minus C1 by R plus C2. Okay. And then again you will get certain equation T minus TW minus T naught is equals to something you will get here. I don't remember it now, and it is not needed. They have never asked this, never. Even today in last 30 years, I don't, maybe like there is 1%, 0.01% chance that I may have missed it. Otherwise, as much as my knowledge goes to last 30, 35 years, they have never asked any question from this. Okay. So this is again parabolic. Okay. So you need to remember one thing. I will still summarize it lastly. What is the last summation? That if steady state, one dimensional without heat generation case hai, if this is the case, then Cartesian coordinate, cylindrical coordinate, and spherical coordinate. Okay. This is what? This is this. Okay. This one. Okay. So this is linear. What is cylindrical? What is cylindrical? Tell me very quickly. No. Why? Come on. Logarithmic. And this is hyperbola. Okay. And steady state, one dimensional with heat generation. If this is the case, then Cartesian ho, cylindrical ho, या spherical ho, everything is parabola. ये है आपका 1 mark question. This is anything will come from here. 1 mark gate question. Anything could come from here. Or PSU में तो it's very important. Okay. So this is how I have summarized the today's lecture. Okay. Now whatever I have done here in these 3 slides. Okay. In these 3 slides, I could have done the whole lecture. Okay. I did not need any derivations to do because in gate derivations are not important. So with a little bit more details, I could have finished the lecture much earlier today. But why did not I do it? For example, if they have twisted the question and you need to do the derivation, that derivation will not be this long, but it will be certain portion, a little bit portion out of this. But you need to know the steps. First of all, find out First of all, you need to know the general equation, then apply the assumptions. Okay, let me summarize this again one more time. Okay, I do not have space. Let me summarize it here. What are the steps that you are going to follow? First, generalized equation, then apply the assumptions. Apply the assumptions, whatever assumptions they have asked. Then determine temperature distribution equation. Then boundary conditions and apply to find C1 and C2. Okay, and then you put this again back here and then calculate dt by dx or dr or whatever and put this equal to 0 to find out location of maximum temperature. Yes, Tmax. That is the general steps. So whatever comes in question, although never, like very rarely, tomorrow we are going to solve questions, then you see what level of questions. So do not get demotivated because of all the derivations. Okay. Tomorrow we will do questions of these, all the numericals that have been asked. So you will get an idea what type of questions are asked, in how much detail you need to go in terms of derivations, in terms of solutions. Okay. So, but you need to know the concept, because knowing the concept is important. Then you need to filter out based on what type of questions they ask in the exam. But you cannot skip the concept as it is. You need to understand the concept. Chalo. So I think this is all for today's class. Thank you very much. Okay. And we will meet tomorrow at the same time. Right? So I hope you liked how was the class for today. Did you like it? I know that it was a little boring, but it is mathematics. It is the sense of mathematics. I cannot do anything about it. Okay. But I promise you, this is the only session in which we have only done derivation. Never, we are not going to repeat. I don't think that there are any other derivations in this. Convection, yes, there are derivations, but we are not going to do that because there is a reason. Why? Convection is very rarely asked. Whatever is asked, you can do it without those derivations. Okay. Derivations are important for ESC, and I think you are not targeting ESC anyway. Okay. So we are going to focus convection as it should be covered. Okay, not extra things. Because first of all, convection is not important from gate point of view. Very small one line questions come from convection. Okay, so we will cover it like that. Conduction is very important. That's why we have done derivation. Okay, I cannot skip the derivation in conduction. Okay. So I hope you liked today's lecture. How was it, Sean? Okay, Sean says good. Sahil and Shruti, how was the lecture? Did you like it? Okay, thank you so much. चलिए, तो I would recommend that you revise. It was interesting. Okay, thank you so much. That was not expected. Okay, so I hoped it was interesting. But ठीक है, I tried my best to do all the derivations. ताकि at least you get, okay, you like derivation. Okay, then it is an exception for you. चलो, ठीक है ना? So ठीक है. Now what do I recommend? Whatever we have done till now, please revise all the formulas, please revise all the concept. Tomorrow we will do numericals. Okay, and I want you to do not get confused on the formulas, otherwise you will not have fun doing numericals. You will get more demotivated. I don't want that. Okay, if tomorrow's session is good for you, that means you will develop motivation in heat and mass transfer, because as soon as you start solving numericals on the concept that you have already learned, then you will get interest in that subject. You will go deep and deep and deep. Okay, so please revise your concept, write down all the formulas, write down all the formulas on the separate sheet of paper. Okay, start making short notes. It's very important. Start making short notes. Okay, and then always revise those short notes. Keep modifying those short notes as well. Okay, and I don't know if I am allowed to, but I have done a lecture on how to revise your concepts or revise your subjects in last, what should be the 6-month strategy, although we do not have 6 months now, but I made that video like in October, so it was valid that time. But at least you will get some idea on how to make short notes and all these things. It is on YouTube. If you search preparation strategy for GATE 2023 by Vipin sir, maybe you will get it. or revision strategy. I don't know. Just search it on YouTube. If you don't get it, let me know. I'll share the link. Okay. So you will get the idea of how to make short notes as well. Chalo. And the revision strategy. At least 3 revisions are required for each subject. At least 3 revisions. So plan accordingly. Chalo. So it is the end of the class. We will meet tomorrow at the same time. I'll see you tomorrow. Thank you so much. Tata. Bye bye. Okay. Thank you. Thank you, Sean. Thank you, Sahil. Shruti. Thank you.